Oh, it's live. It's working, I think.
Yes. Okay.
Great. Thanks.
Apologies. I have no idea why that didn't work straight off the bat, and I don't think we've changed a single setting, but it is now working. Over to you, Laura.
There's no other. Okay, can everyone hear me okay? Alistair, can I be heard okay? Or am I?
Yeah, sorry, you just cut out
sound?
for a second. You just cut out for a second.
Okay, cool. Right. So welcome everyone. Sorry it's a bit delayed. We're 8 minutes in. But thank you for your patience and welcome to our third lecture of the month, which our free lecture, which happens every third Thursday of the month. And I will be a bit further than I was. I just did the whole introduction. Yes, tonight our guest is Martyn Wells, who is head of the who is the optic lead for the MIRI on the famous James Webb Space Telescope. And I see that my internet is really bad, so I'll just give the mic to Martyn Wells, and thanks for being here.
Okay. Right. Okay, so can everybody see my screen then? That's okay.
Yes, Martyn, that looks good.
Okay, and you can hear me. Right, so I'm Martyn Wells. I work at the UK Astronomy Technology Centre on Blackford Hill in Edinburgh. And so about, when was it, 21, 22 years ago, Julian Wright, who is the lead for the mid-infrared instrument on JWST, invited me or asked me to be the optics lead. So that meant that I was responsible not for necessarily designing stuff, but for making sure that the stuff that everybody else designed worked together and worked with the telescope. So, but I think because the JWST now it's in orbit and it's very topical, I've just got a few slides of where we are with the commissioning. So, but to start with, this is a model, a full-size model of the telescope that has been erected in a number of places. And so, you know, that you don't get, we'll never see a picture of this. There's no cameras and the telescope is all in the dark because of these sun shields. But I thought this picture was good because it shows you the scale of the observatory, how big these sun shields actually are, and also the size of the telescope. So this is a summary of the James Webb Space Telescope. So it's now in orbit around L2, 1.5 million kilometers from the Earth. The primary mirror is 18 hexagons ranged, or it's 6.6 meters across, and they're all now being aligned to submicron accuracy. So I've just got a couple of slides of that in a minute. And the operating temperature is 40 K or minus 233 centigrade, and as was announced a few weeks ago, the lifetime is now expected to be considerably greater than 10 years. And so there's 4 major science instruments on that. So there's a near-infrared camera, which is now being used to align the telescope, a near-infrared spectrograph that was built by ESA. So that's a wide scale or 1 to 5 micron spectrometer. And then the thing I'll be concentrating on is the mid-infrared instrument. And then finally, there's a fine guidance sensor and the near-infrared imager. So the news today is that this fine guidance sensor has been turned on and it's all working. So you almost get daily or at least weekly updates on things being turned on and everything seems to be working, which is all great news. But JWST has been a long time coming. As I said, I started 20 years ago, and this was a launch date. So in November 2017, they were expecting a launch date a year or 2 years later. But here we are now, what are we, 2 years after this. So there's been considerable delays, but as a result of this, I think the success of it has shown how they've made sure that everything is all working, but it's also enabled the astronomers to refine their observing programs to make very efficient use of the resources. So I'm sure some of you have seen this. This is the initial alignment of the or the initial image that they got from the telescope. And what you see here is 18 separate images, one from each of the segments. And so they've identified which segment belongs to which image, so they know which way to drive each of those segments to bring them all together. And then when they've brought them all together, they'll have 18 images all piled on top of one another, but the wavefront is not necessarily such that they combine to increase the spatial resolution. So that is why that process is taking the next couple of months to achieve. And then this is the image of the primary mirror itself, where the starlight is illuminating, well, the starlight is illuminating all 18 of the segments, but only one of them, the light is only getting through to the detector from one of them. So this is this is looking at the mirror of the telescope itself illuminated by starlight. And this is where we are. So in terms of temperature. So you can see that the green line here is the primary mirror. So the primary mirror is getting pretty cold, down to -223, so about 40 Kelvin. But MIRI at the moment is warmer because it has to be, the final aim is that we want MIRI target down to only about 6 Kelvin, but for the moment, because it's thermally insulated from the rest of the observatory, therefore it's not cooling down with everything else. It's elevated above it, so it will eventually get down, and it has its own cooler that I'll come on to later. But this is a sideline about passively cooled telescopes. So there've been a number of missions which have taken liquid helium or other gases up into orbit to keep them cold. But my colleague Tim Harden, he was working at the ROE when I arrived 30 years ago, and so this was a meeting that was held the month after I arrived, looking at the idea of passively cooled telescopes. So the universe is cold, only 2.73 Kelvin. But if you can shade yourself from the sun, you get very cold. And this is the idea that Tim generated, and we had a workshop there. And then for this work, he was awarded this NASA Exceptional Technology Achievement Medal. So the whole basis for making a cold telescope in orbit was actually started here in Edinburgh, and this is the proceedings of the the conference, and you may recognize S.J. Bell Burnell is Jocelyn Burnell. So I was surprised to meet her when I arrived in Edinburgh. So I'm going to be talking about MIRI, the mid-infrared instrument on JWST, and the other instruments work at a shorter wavelength, 1 to 5 microns, but MIRI extends this going from 6 microns out to 28 microns. But this longer wavelength means that a colder temperature is needed so that the detectors are not swamped by black body radiation from the instrument itself. So MIRI operates at 6 Kelvin and it's wrapped in thermal insulating blankets, and it has its own cooler that I'll show you a picture of later. So MIRI consists of a number of subsystems. You've got the 4 optics, which brings the light from the telescope focus through to the other, and divides it up into the various sub-instruments, and that also provides calibration light. And then there's one major unit is an imager, but has coronagraph masks on its entrance aperture, and that has also a prism low-resolution spectrometer. And then there's the medium resolution spectrometer, which works from 5 to 28 microns, and that was the instrument that was led by Julian Wright at the observatory here in Edinburgh, and that I was I was the optical engineer for. So that's the picture that I grabbed off the web today, showing the components of MIRI. But if you go into the detail, so you're probably not going to absorb any of this, but this just shows you the complexity of MIRI. They've got imager subsystems and all the gratings for the spectrometers, detectors, and then insulation. So there's a whole lot goes into it, and as I said, it took us quite a long time to design and build this thing. So let's look at what MIRI consists of. The light from the telescope is focused into this input optics system. So there's a mirror here that takes the light from the telescope and reflects it up into the instrument. So the main focus of the telescope is somewhere in here. And then the first component is an imager that was built mostly in France. And then the other instrument is the spectrometer, and that consists of a spectrometer preoptics that divides the light up that I'll show you, and then the spectrometer main optics that were built in the Netherlands. The other bits of it were, the detectors come from America, the deck that everything is bolted onto was made in Leicester. The carbon fiber legs came from Denmark. So it was a true international collaboration, and the job that we had in Edinburgh and with our colleagues at Astrim was to make sure that when all this came together, it was all aligned and would work as we hoped it would. So I've just now got some pictures of MIRI as it was built. So that previous slide was just the concept, and this is what the actual hardware looks like. So you've got these carbon fiber insulating legs, because we want MIRI to work at the colder temperature of 6 Kelvin, whereas the bottom of the legs is the same temperature as the rest of JWST instruments, which is about 40 Kelvin. And then the light comes up from below, which you can't see, but then this is the imager, and then you've got the deck here, and then the spectrometer on top. And this is the instrument as it was when it was delivered to Goddard Space Flight Center, where it was integrated with the rest of the instruments, showing it wrapped up in its thermal insulation. So the MIRI imager is, now this should show as a video. So this is a video produced by ESA, which describes the operation of the imager. So I'll just run this, and maybe I'll stop it and say when we get to. So this is the MIRI imager rotating, so you can see all the various parts of it. Yeah, so the light comes in from the telescope, is focused down, and then reaches the focal plane. Excuse me, I've done these labels around the wrong way. This is a spectrometer. So the light comes through the spectrometer and is split up into multiple wavelengths and the different channels, and then it goes through a slit, and then on the other side of the deck, goes into two spectrometers for the different wavelengths. So these spectrometers are built by in the Netherlands, but they all had to be integrated with the optics made here in Edinburgh. So that was a spectrometer, even though this is labeled imager, but we'll now go on to the imager. I need to go on to the next slide. Right, okay, so now we're going to look at the imager. Introduction again. Right, so we've got a bigger beam, bigger field of view, and then the light enters through a focal plane mask here, and then imaged through the filter wheel, and then via 3 mirrors onto the detector. And so you can have the filter wheel that I'll show you a video of in a minute, and then different colors and different capabilities in that filter wheel. So that was the 2 videos produced by ESA. And now what I've got is a rather fun video made by colleagues in the Max Planck Institute in Heidelberg that show the imager filter wheel. So all the different capabilities, and you got filters for imaging, you've got coronagraph masks if you want to look at objects around stars. So there's a lot going on, but you can see how this very delicate mechanism that just precisely aligns the wheel, and it all moves with the minimum of energy, because MIRI is cold. You don't want to put any heat or minimize the heat you put into it, otherwise it can get warm. So those are the videos of showing the various parts of the imager. Right, so let me just move on. Right, so now looking at more detail of the this is the part that was built in Edinburgh. So what we have here is a spectrometer preoptics. So light from the telescope comes here, and then we saw in the video that the light is split up into different bands. And what these mirrors here are, they're dichroic mirrors, so they reflect short wavelengths and transmit long wavelengths. And you end up, after going through 3 of these, you end up with 4 different bands. And then these go into these integral field units. And what the integral field unit does is to take a rectangular field of view here and reformat it until it comes out as a slit that we can then use as the entrance to a grating spectrograph. So this, as you can see, the layout is somewhat complex, and it took more than probably, I think my colleague Peter, it took about a year to make sure that everything was there and everything fitted. And this is a more schematic design of this spectrometer. So the light is from the telescope is come with these dichroics. It's split into different wavelength bands. So you've got the first band is, where are we? Yeah, I can't see, but you've got 4 bands working from 5 to 28 microns. And then once they've split up, they go through these integral field units to make the rectangular field of view into a slit. And then after that, then this is a schematic of what happens to the light. It comes onto the gratings and then goes through the integral field unit, onto the collimator, back onto the grating, and then through the camera to the focus. And this happens 4 times. And one of the complications was that we had to make sure that these dichroics and the gratings were on a mechanism that was built in Germany, but we had to make sure that the gratings that were coming from the Netherlands and the dichroic wheels coming from Edinburgh, when they were all mounted, everything was aligned. So that took me and my colleague Phil about 3 months to specify that and make sure that it was all working. So the spectrometer preoptics, although this is the spectrometer built in the 2 arms of the spectrometer built in the Netherlands, and you can see that the light paths are multiple crossings of the light paths, and there's a lot going on within this confined space. So because it's a space instrument, volume and mass are critical. So it took some time for colleagues in the Netherlands to make sure that this all fitted and met the weight specification and the image quality. So that was a considerable effort as well for just, for that bit. So now I've got some slides of various components. So this is what we call an image slicing mirror. So this mirror is made of aluminium, but you can see it's got a number of facets, and these facets each have their own tilt on them, but they're curved. And these were made on a diamond turning facility at Cranfield University. And so they had to mount this on their machine to make one of these mirrors, and then move the whole thing and then make the next mirror. So this has got 18 slices, and it took them some weeks to make this mirror. But it does mean that we can take a rectangular, so we could for example, put a galaxy on here, and then each of these mirrors would then slice the image up, and we can form the entrance slit to a spectrometer with them. And then here's some slides of all the various components of sub-assemblies of MIRI. So, and the international nature of this. So there's a cover which was built in Switzerland. And this has a critical point, because when everything else is cooling down, you want to make sure that any residual dust and gas which is floating around whilst the whole observatory is cooling down, you don't want any of that to get into MIRI. So at the moment, this contamination control cover is closed to prevent contamination from the rest of the instrument. But as you could know, as is obvious, at the end of this, it has to open. So there's redundant mechanisms on here to make sure that when they do request it will open, it will. So I think it's already been, it was opened for launch, and then it's been closed, and then will be open again in a couple of months' time. There's a filter wheel built by Max Planck Institute in Heidelberg, which we saw the video of. The main deck on which everything is mounted, University of Leicester. The legs made by in Denmark and by Leicester University. The input optics built in Liège in Belgium, as are the electronics. The detectors made by Jet Propulsion Lab in NASA Jet Propulsion Lab in California. So there's a whole lot of going on, and so I had colleagues at Leicester University who were responsible for making sure that all these mechanics all bolted together, aligned, and then my job was to make sure that when they were bolted together, all the light reached the detectors all aligned, and with no vignetting, no losses. And then going on to more components, this is the spectrometer preoptics made here in Edinburgh, and you can see the gratings in here. So the gratings were made by or supplied by the Netherlands, and then we bolted them onto the wheels. There's a calibration source that was made at Queen Mary University. Spectrometer main optics, as I said, this is the made in the Netherlands. The imager, which I'm not talking so much about, this was made by CEA near Paris. Filters provided by Dublin and Stockholm, and then the detectors, as I said, by JPL. So it's a truly international collaboration. And right, so this is my colleague in the ATC. I'm just bolting things together, so you can see the scale of the thing from compared with him. It's handleable, but you have to be very careful about making sure that it doesn't get contaminated, and so obviously you have to build the thing, or put it or bolt it all together in clean room conditions. And here showing the filter, the grating wheels. So each channel has there's 4 channels, and each operate in 3 different positions. So we have to divide the wavelength band up into 12 sections to make sure that we get all the wavelength range we want at the resolution we want. And then here's a more detailed view of the layout, which I showed you a schematic of, showing how all these mirrors all had to be precisely aligned when they were mounted. And then, so this is showing the individual filters that go on the filter wheels. Inside here, you can see that there's a coil which holds the filter in position, but it stops it. So it's not it's not clamping it tight, which did cause a breakage in our first design, but this one has to be sufficiently strong that holds the filter in place, but under vibration, it doesn't allow the filter to knock into its mount and break. And then this is, so as I said, most of the instruments on JWST are working at about 40 Kelvin, but because MIRI is working at a longer wavelength, then it has to be colder and it has to work at 6 Kelvin. And to do that, you need a cooler. So previous space missions have taken up a spacecraft full of liquid helium, but that has a finite lifetime. And so what our colleagues at the JPL have produced is a closed cycle cooler. And this has 2 reciprocating pistons in here, which compress the gas. And then that is sent down very narrow lines to MIRI, where it expands and then cools, and then it's all sucked back in again. So you can see that this is quite a sizable piece of equipment, and this is all sitting on the warm side of the telescope of the sun shield. And then so that has yet to be, I think it's been preliminary tested, but it's yet to be proven to show that MIRI works. So in the next month or so, when everything else is cold enough, then this closed cycle cooler will be turned on to bring MIRI down from its current 40 odd K down to 6K. And this is my selfie. This is me sitting in the clean room at Goddard Space Flight Center. So we had to make sure that MIRI, when it was mounted onto the along with the rest of the instruments, it was aligned so that the light from the telescope would go all the way through the MIRI instrument and reach the detectors. So that took considerable effort to make sure that not only was MIRI right, but also the way we were measuring things were right as well. And then finally some data. So this is what we call this an integral field unit. So this mirror that I showed you before, this, as I said, this splits up the light from a rectangular field of view and makes it into a slit. And so each of these slices corresponds to one of these spectra. And we have 4 channels working from 5 to 28 microns. And so we've got, so in these images, you've got spectral information down the way, and then spatial information along the slit, along in one of these spectra. And then, but then what you can do is to combine these together to produce a spectral image. So this is all shown, as you can see, it's all working, but we've got to make sure the next step will be when all this is working in orbit and we get spectra of real objects rather than just a calibration lamp. At the beginning of the talk, I showed you an image of the pupil, a pupil image of JWST taken by NIRCam, but we also have this capability in MIRI. So MIRI has a pupil imaging lens, which means that it can take an image of the telescope pupil superimposed on a mask which represents the internal alignment of the instrument. So when that image is taken of using this pupil imaging mask and lens in orbit, we'll know how well MIRI is aligned to the telescope. And so I spent quite a lot of time making sure that MIRI internally and externally to the rest of the telescope was aligned. So it was only, I think it was about 5% of the diameter. So it's aligned to within 5% of its diameter. And so I'm looking forward to seeing how well it's all aligned, having been launched into orbit. And finally, something you may recognize here is knife edge focus testing. So when we were testing MIRI at, so this was at the Rutherford lab near Oxford, we needed to know whether MIRI, the internal focus of MIRI was, or rather the external focus, when images were in focus on the detector, whether this corresponds to the definition that we'd written. And so what we did was some knife edge testing, and each of these lines, top to bottom, correspond to a different focus. And I think if you look carefully here, at the top, the shadow comes in from the right, whereas down the bottom, the shadow comes in from the left. And then somewhere in the middle, just about here, then the shadow appears all over. So this was a test that I devised so that we could test the focus of MIRI compared with the rest of or the external references. But I was quite pleased at being able to use this classical knife edge test to do that test. So that's my talk, and I will welcome any questions.
Laura, do you want to give it a go, or do you want me to? You're muted. Well, Laura's she can't unmute herself. She doesn't have those privileges. Yeah, so while I'm unmuting Laura, thank you, Martyn. That was a wonderful talk and very interesting. I have a list of questions here, but Laura, please take it away if you would like.
All right, I don't have much to add, but thank you. And most importantly, I learned that it's not MIRI, it's MIRI now. So thanks for that. That was great. We'll take on questions. So please, members, feel free to put them on the chat or to just raise your hand so that you can ask your question directly. And we also have people on YouTube. And I think we'll, yeah, we've got a couple of questions on YouTube already. I'll take one from Eva Beckesy, who says, "Hi Martyn, was a pleasure to watch this lecture. I am learning about spectroscopy and would be interested in the spectral images we haven't seen in mid-infrared wavelengths."
So you mean the images, the reconstructed images?
I'll assume that's just a question that's been written.
Yeah. So what I was showing you in the slides, which showed you all the stripes of the images. So from that you can reconstruct an image at different wavelengths of an object. So some people are interested in the spectra of individual points within the image, but some people want to have images. And so what you can do is you can produce images which show you at in the light of say the hydrogen emission from an object. You can show that the distribution of hydrogen in an object using this technique. And the nice thing about the having an imaging spectrometer means that you may be looking at hydrogen emission at different redshifts, which means that if you had just a camera with a filter, it would only have one wavelength, so you couldn't look at it in multiple wavelengths or multiple redshifts.
All right, thank you. I'll take Ewan's question, and then we have Craig, who's raised his hand. So from Ewan, we have, how far through the setup process is the telescope?
Okay, so the telescope, all the mirrors are deployed, and so as I showed at the beginning, they've got 18 images, but they've got to go through quite a lengthy process now to make sure that all those images are in focus, and then put them on top of one another and make sure that all the light from all those segments all join together interferometrically. So it's not just photons, but we're dealing with wavefronts rather than thinking of just adding up the light. You're combining wavefronts from all those individual segments, and when you do that, you effectively increase the effective size of the telescope to the full 6.6 meters, and then you get diffraction limited for a 6.6 meter telescope. All
right, thank you. Next we have Craig, who's raised his hand.
Hi, Martyn. A lovely lecture. I haven't had one as detailed as that for a while. Well, what I'm asking the question here is the temperature, 6K. Now, you have on your instrument a rotating filter wheel.
Yes.
Yeah. How do you keep the temperature? Will there be any temperature impact of rotating that wheel, given you're operating at 6K?
Well, yeah. So as I showed you in the video of the filter wheel moving, that has been designed so that when there's a very small pulse of energy goes in, and that small pulse of energy is, you've got about, I think 60, 70 kilograms of aluminium. And so those small pulses of energy, they'll heat the aluminium, but only by a fraction of a degree. So it's just a matter of the energy input is small enough, and the mass of the aluminium that it's going into is big enough so that the fluctuations are quite small.
Are you expecting any interruption to the observation as you change filter wheel?
Oh yes. So you'll be observing, and then you move the filter wheel, and then stop integrating, and then move the filter wheel, and then take the next image.
Excellent, thank you.
All right, great, thanks, Craig. Next question is another question from Eva Bekesi. I hope I'm pronouncing this okay. How will scientists see the filtered images in different wavelengths?
Sorry, how will they use them?
How will they see the filtered images in different wavelengths?
So the images will all be, so they're all loaded into the electronics of the MIRI electronics, and then those go through all the communications, and then they're downloaded. So I think, is that what the question was about?
The question was on YouTube, so hopefully we'll get an answer with a bit of lag. But yeah, in the meantime, we've got Julian who has a question, and I think he'll ask directly here.
Hi, Martyn. Thank you for that incredible level of detail. Absolutely fascinating. I understand how the spatial alignment of the 18 mirrors would work by moving them individually to get the coincident image on a pixel and so on. Could you explain more detail how you do the wavefront alignment, please?
So, well, this is, I was going to say it's beyond my pay grade. this is the clever guys at NASA are able to take the individual images and then take them, each of them individually, through focus, and then they find where the best focus for each of them is, and then combine them, and then what's the name? I forgot the name of the process now. But there is a process of taking images through focus, and then you can then combine these. Well, I think they start off doing them pairwise, and then add another mirror in. So you get two mirrors together operating, and then you add a third, and so you do it piecewise until you've got all 18 going.
Mm-hmm. So you're looking for constructive interference, is that correct?
Yes. Yeah.
Right.
Yes.
Okay. Fine. Thank you.
All right, thank you. And for the question on filtered images in different wavelengths, we got a thank you from Eva. So I think that was the correct, what the expected answer. We also, I see Alistair's raised his hand. I'll just take another question from YouTube and then you can go ahead. Paul Kent asks, at 6K, will there still be a considerable background noise floor, or is 6K enough to virtually eliminate noise even for long exposures? And what exposure time would be typical for the MIRI imager? And he adds, excellent talk.
All right. So the 6K, so we calculated at the beginning of building MIRI that 6K was needed for the detectors, because the radiation from around the detectors is broadband. You just get 2 pi steradians of light falling on the detector, so it has to be cool at 6K, otherwise it's swamped. But we did calculate that the rest of the MIRI, apart from the bit around the detector, could be as warm as 20K. But it was just much more simple to build everything all, make it everything aluminium, and make sure that it was all at the same cold 6K temperature. So that was a decision made early on, that rather than having different temperatures in MIRI, we would just make everything 6K. So the detectors need to be 6K to make their internal noise low enough, and for the surrounds, so that the black body radiation surrounding them didn't swamp the detector. But it was just easier to make everything else 6K as well on those insulating legs.
All right, thank you. I'll let you get the next question, Alistair.
Thank you. Yeah, again, thank you, Martyn, for that talk. It was very interesting. I've written down a few questions here, but I think I can summarize them all into just 2 points. One is, these light paths for this folded light paths look complicated. I think I've tried to liken it here to playing 3D chess with a grandmaster, and you just kept playing until you won a game. But what is the resolution of MIRI compared with other currently available detectors, and how worried or afflicted would it become if it were, or how worried about contamination of these optics are you in terms of loss of resolution?
So the resolution of the MIRI spectrometer is about 3000. So that's what we achieve in spectral resolution. And so what was the other question about contamination on the mirrors? So yeah, so that we built and delivered MIRI in 2012, and since then it's been sitting under in NASA labs, but wherever possible the contamination cover is closed, but there's also a clean dry nitrogen feed that is been constantly flowing through that to make sure that there's excess pressure within MIRI. So air is flowing out of MIRI all the time, rather than an ingress of air and accompanying dust. So it's, you know, keeping something clean for 10 years was not a trivial not a trivial job.
Yes, I can definitely appreciate that. It's
and you're going to
extremely
appreciate
relevant
yes
for our joint project. Yeah, so thank you for that.
Awesome. We've got another question from Craig.
Hello. Yes, just a very simple question for you, Martyn. Basically, I'm asking, will there be any maintenance visits to the JWST, or is that basically out of the question, given its position at the L2 point in space?
Yeah, so I think that I did hear some sort of talk of replenishing the fuel tank, or for doing the pointing. So I think that is going to be the limiting factor. But you know, Ariane Spas put a whole lot of effort into making sure that MIRI, the JWST, got to its orbit with using the minimum amount of propellant. So now they're confident that they're going to get more than, you know, considerably more than 10 years. But then I don't think there are any feasible schemes for actually going out there. So I think it will be, it's just until the gases used for pointing run out. So
the telescope's at its final configuration. It's not going to be modded in the coming years.
No, there's no plans for that. You know, whether in 10 years time and everything is working finally, and they would like to keep going for another 10 years, and they would attempt something like that, but I don't think so.
No plans.
Yeah.
Okay, thank you.
Great. Thanks, Craig. Now we've got a question from Jim, if you want to ask yourself.
Hi there, Martyn. Thanks very much for that. That was fantastic. Really fascinating stuff. And I'm very much a beginner to all of this astronomy malarkey. I'm one of the more recent members of the society. I was wondering about basic fundamental telescope arithmetic, because we concern ourselves with focal length and focal ratios and those sorts of things. Are those an issue for MIRI, or is it a total different technology? Because I was trying to follow the light paths and the different frequencies of light and thinking they must be all over the place. Am I wrong?
Well, so the telescope delivers a focal plane to the entrance to the instrument, and then what happens in the instrument, we have to make sure that we transfer all that light, which I think is an F13 beam from a 6-meter telescope. All that light then has to be compressed down into the detectors. Are only what about I forgot, the detectors about 10 centimeters square. So all that light from the 6-meter telescope all has to be focused down onto this quite small detector, and going through the some of the small, the sizing mirror I showed you is only 2 centimeters square. So a lot of effort was making sure that all that light from the telescope got through all the instrument. It was, yeah. So that was my job for 10 years, making sure that everybody was aligned, and so that light bouncing off a mirror didn't just go off onto into the side of the instrument.
Yeah, that was my other part of the question, was wondering how on earth do you prepare for a job like this? Because this is just such a once in a lifetime opportunity, I guess.
Yeah, well, I did work on a previous ISO, which was another space mission, but my job there was considerably less. But no, I wasn't alone. So there was a team of about 10 of us who were overseeing the build of MIRI. But each country had, their own team. So I think there was probably 10 in France, 10 in the Netherlands, half a dozen in Belgium. So there was lots of teams all over. And so what my job was coordinating this and making sure that everybody built to the specification that we gave them.
Amazing. Thank you. Is that all for you, Jim?
Yes, thanks.
Great, fantastic. And we'll take just one last question because we've occupied your time for quite a while now. And it will be another question from Julian.
Hi, Martyn, thanks again. You mentioned that the detectors are at 6 Kelvin. Does that mean that the detectors can't image the cosmic microwave background, which is about 2.7 K? Would the light from that or the energy from that be swamped out by the inherent heat within the detectors, please?
Yes, yeah. So that would be the case. And it's also, you've got radiation from the telescope mirrors. So the telescope mirrors are considerably warmer. They're more like 40 K.
Okay.
So the satellites that went out to L2 that were looking at the CMB, they were all cooled directly with liquid helium down to a few degrees. So you need the whole telescope at that temperature to so the cosmic background is not swamped by the telescope itself.
Sure. Yeah. Okay. Thanks. Thank you. Thank you.
All right, great. Well, thank you so much, Martyn, for this lovely talk. We hope that we can have you again and hopefully in person in Glasgow. That would be amazing. Yeah. And obviously there will be much more to learn, I assume, as the mission keeps going on. And yeah, and thanks for answering all the questions. And
that's okay. I really enjoyed it. It's good, yeah. To go back, so I stopped working. Well, I haven't stopped working. I'm still working on MIRI, but most of my work finished in about 2013. But it all came it all came back. With the launch, everything came back again. So it's great to be able to talk about it.
Oh my goodness, that's such a long span.
Yep.
Very exciting anyway. And yeah, it's everyone's saying thank you for the talk and that it was excellent. So yeah, we really appreciated having you here. And
so I can produce a PDF of the slides. So I'll send those to Alistair, shall I?
Yeah, amazing.
Yeah, and just a final comment. David Deegan says hello, Martyn, and apologizes for not being able to be attending, but he's looking forward to watching the recording. Right. We might do a little editing first, but yes, I think everything has ended smoothly. Thank you.
All right.
Yeah, thanks so much for your patience.
That's all right. Yeah, I enjoyed it.
Stop the recording now, I think, for
Thanks very much.
Yep.